Коллеги, давайте начнем. Вроде как у нас количество участников стабилизировалось. So, I'm not sure that all in our conference can understand Russian. Moreover, we have 7 participants in YouTube, 6 participants in YouTube stream. But okay, Alexander, up to you. You may give a talk in English or in Russian as you wish. But anyway, I'm glad to see all of you in our 53rd seminar. And I'm glad to introduce you our speaker, Alexander Alodjants from ITMO University. And he will talk us about quantum metrology beyond Heisenberg limit with bright quantum solitons. Please.
Yeah, thank you very much, Konstantin, for invitation. I will speak in English because I hope that maybe somebody will join us from the outside, and I think it will be much better for all of you. Today I will speak about quantum metrology beyond Heisenberg limit with bright quantum solitons, and here you can see the plan of my talk. In particular, I will give a short introduction. No, I think maybe not so short, but I will give you introduction about quantum metrology tasks and state of the art. Then I will speak about quantum metrology approach in optics and in atom optics with Bose-Einstein condensates. Today I will speak about quantum metrology with condensate solitons, and this is a new area of studies. And I will discuss why these quantum solitons preferable for metrological tasks. Also, I will speak about quantum soliton Josephson junction device as a new powerful tool for quantum metrological applications. Finally, I will report about Lossy quantum metrology with solitons, quantum Fisher information approach. This is a general approach for current quantum metrology. And finally, I will discuss about possible experimental observations by means of current experimental achievements. In summary, I will represent some slides about our group and how people is involved in this process. So first, I would like to stress what is the quantum metrology and how we can understand it. Actually, the aim of quantum metrology is development of the methods and devices to measure some physical parameter or parameters at the level of fundamental quantum noise limit, determined by the source by some uncertainty relations. So if for example, if we would like to measure and estimate some parameter phi, we can consider in very general case this kind of scheme. We have some preparation of the quantum state for the measurement. Then it is necessary to make some unitary transformation for phi parameter. And then at the final step, we have a detection and estimation. And if P operator, for example, responsible for that, this is observable, it could be some observable, the propagation error for delta phi can be determined by using this very simple equation. In fact, it's determined by the fluctuations, by the measured fluctuations of the P observable. And this is also some variation of the P observable. Of course, P observable depends on the phi. And from this point, some different 3 main questions appear. So first, what is the transformation for the measurement and estimation of phi, which allows to obtain highest precision. Second, how we can prepare quantum state of probe measurements precision for phi. And finally, what is the most effective scheme of detection of the P observable? So for the first time, I would like to thanks to this great man who is unfortunately died. It's Vladimir Braginsky. He's a professor at the Moscow State University for a long time. And I think everything is started many years ago from the Braginsky paper, from the Braginsky activity at the physical department of Moscow State University. And in particular, I would like to mention his works related to the gravitational waves detection or measuring gravitation. And then, so this is, as you know, this field of research now is supported by the Nobel Prize for Kip Thorne. And then also the high precision measurements was being predicted and proposed by, for example, for in noise spectroscopy and in quantum spectroscopy, and in particular, I think you're familiar with the David Wineland paper, who is also Nobel Prize laureate. And currently, this topic of research is mostly focused on metrology and sensing. And this is very some new papers, some new papers on this field. Actually, high precision measurement and metrology is on the focus of quantum information science, in particular quantum phase estimation, quantum metrology strategies, quantum nonlinear metrology, which I today report for you. Actually, I would like to mention that my first experience in quantum metrology is happened maybe more than 20 years ago. Here I would like some paper about polarization state, polarization squeezing, how we can use for in interferometry. And now I will speak about some new possibilities for that. Here you can see a very simple device that is Mach-Zehnder interferometer. The Mach-Zehnder interferometer possess measurement and estimation of the some phase factor phi. And how I mentioned it before, if we consider Mach-Zehnder interferometer, here we have a source of input state. Here we have some unitary transformation for the phi, and here we have a detection scheme. And this is a three-step measurement and estimation of some phase phi. So if we speak about typical noises, we can standard quantum limit. In particular, if we speak about standard quantum limit, we can take into account Mach-Zehnder interferometer with the coherent probe. This is a very well-known scheme for the measurement. Due to the fluctuations of the laser field, we can obtain also fluctuations, or I can say some error of the measurement and estimation of the phi parameter. And here you can see how it is defined. So it is limited by the fluctuations of the laser field inside the interferometer, and this is a phase and phase difference and photon number uncertainty relation that relevant to this scheme, and standard quantum limit for phase measurement states that it is impossible to, with coherent light, it is impossible to measure phase factor, which only with it is possible to measure phase with this limit. It is limited by the standard quantum limit. So in quantum metrology, we can try to enhance this scheme by using, for example, quantum state of the source. And here you can see metrology with noise, quantum noise suppression. So here, typically this scheme is based on Mach-Zehnder or Michelson interferometer. I hope Michelson interferometer, I think, is a device that is completely analog of Mach-Zehnder interferometer. And here you can see that we use not only a laser field, a coherent state, but also squeezed vacuum at the input of this scheme. And finally, you can see what is the precision, how we can measure this phi. This is accuracy, how we can measure, how we can estimate the phi, and this is the precision. This is beyond standard quantum limit. And already I would like to mention that this kind of measurement is already used in typical LIGO, KAGRA, and other interferometers, which are relevant to gravitational wave detections. So here you can see the picture, how coherent noise and how quantum or squeeze state can enhance the measurement and the measurement of the signal. But what is very important, it is very important that this system, this method is limited by the by using a very large number to implement this measurement. It is necessary to have a large number of squeezing parameter, and now in the labs it is restricted by the number of 15 dB. And it is also necessary to use a large number of the photons which are relevant to this measurement procedure. Of course, we would like to obtain precision much higher than this limiting case. And here I would like to summarize this short part of my talk. In particular, according to the linear metrology, we have this kind of unitary transformation for the phase. And in particular, the error of the measurement and estimation of the phase is limited by the standard quantum limit here from the one side, and on the other side is so-called Heisenberg limit. The Heisenberg limit can be achieved by using so-called null state. Actually, null state can improve standard quantum limit, and recently there exists a lot of some papers where it is possible to find some schemes how we can create null state. But what is the very important limitations for these schemes? Very important that with these schemes, scientists obtain a small number of the particles. The number of particles is limited by 2 or 3, maybe 4, and I don't know, not so much. Because null state typically is very fragile, and it is rapidly decohere, and it is very interesting and very important. This is a very vital question. Is it possible to obtain null-like robust state for mesoscopic, like 50 particles and more number of particles? So what is the null-like? I will tell you during my talk. Actually, recently, also very interesting direction that relate to the quantum metrology is nonlinear metrology approach. And nonlinear metrology approach also can be useful to obtain so-called super Heisenberg limit. Super Heisenberg limit means that here we have this unitary transformation. M is some number, and this is completely nonlinear transformation for the phi, for the parameter that we would like to estimate. And here you can see you can see that even with the coherent two-mode probe, we can obtain super Heisenberg limit, the limit beyond the Heisenberg level. And if we use, for example, Nun state, in this case, we can obtain maximally available super Heisenberg limit that can be that you can see on this from this formula. So actually, if we use, for example, Kerr-like medium for which M number is equal to 2, we have some input state, some output state. This is nonlinear medium that perform this unitary transformation. And in this case, we can obtain, instead of this equation, we can obtain these inequalities. And here you can see that actually we can obtain super Heisenberg limit with the Kerr-like medium. But also very interesting question, can we beat this limit in practice? So it is the Kerr-like, and today I will discuss these two very important problems. For the first of all, I would like to mention that I consider atomic version of the Mach-Zehnder interferometer. Here you can see, in particular, I can use two-mode atomic states, and in particular, we consider two-mode Bose-Einstein condensates. Why we use Bose-Einstein condensates? We use Bose-BC because they possess high nonlinearities, and in this case, it is possible to use mesoscopic number of particles. This is very important for my talk. So if we compare these two interferometric schemes, we can say that rotation on the Poincare sphere corresponds to the field transformation in Mach-Zehnder interferometer. So actually, now I'm summarizing and this part of my talk, and what is my main message that I would like to give you for today. My main message is shown on this picture. First, I consider linear metrology approach, and here phi is a linear phase, and I will show that if we use that, we can achieve Heisenberg limit by using quantum solitons, entangled solitons at the input of this scheme. As the measurement procedure, it is very amazing, I can say, and one of the there exists some advantages if we are able to measure parities or parity detector, we can use that. But how we can see, this is not important restriction. So in principle, it is possible to, if there exist some losses, we can use just usual detectors, two detector scheme. So next, I will discuss about nonlinear metrology approach, and I will show that, for example, phase difference between two quantum solitons, we can measure that with the accuracy which is inversionally proportional n and cube. This is very important because it is shown that even for current technologies, current systems, it is possible obtain this maximal accuracy for the phase estimation and measurement. So now I'm going to the solitons, and here you can see the list. This is about quantum solitons, of course. And here you can see that the quantum solitons, this is not so, this is long, has a very long history already. It started from a famous paper of Lieb and Langer. What is important for us? So if we look at, so you can see that currently solitons consider under the matter-light interaction, and recently people discuss solitons in BC. Here you can see some literature about that, and why BC solitons are interesting for us. They are interesting for us because the solitons can appear for a relevant for mesoscopic number of particles. And here you can see a small short sketch about that. This is a Schrödinger equation, and this is no, I can say that this is a semi-classical limit. Here you can see we consider non-moving bright solitons. And what is important? So solitons are very they correspond to the nonlinear, highly nonlinear objects. They are highly nonlinear objects because you can see that also the shape of the soliton depends on the particle number. And what is also important for us, the phase is proportional to the n square. This is very big difference from usual Kerr-like mediums because this is a Kerr-like medium, but the solution is highly nonlinear. And actually, if we consider atomic solitons, in particular, if we consider, for example, lithium atoms possess negative scattering lengths. And negative scattering lengths means that we are able to obtain this bright soliton solution as the result of our experiment. And here you can see some experiments with bright solitons in atomic BC. And what is also important, that the number of atoms is not so high. So here you can see the critical number of atoms when collapse is appear, because in the regime of negative scattering lengths, atoms are attractive, and in this case, everything is happen should be happen beyond this number of particles, this number of particles. So actually, I would like also to mention that it is possible to tune scattering lengths by using some external magnetic field. This is also very interesting, very important for experiment. And now, so if we consider the solitons with a small number of particles, with not so high number of particles, it is possible to use this quantum approach that we propose in our papers. And what is this now? I little bit explain that. So in particular, if we have, for example, Gaussian state, so we can apply this solution ansatz. And this solution ansatz means that we consider quantum field variable for time-dependent field variable, and classical wave function that characterizes special distribution of the condensate wave function. So this is very typical approach. This occupation of this mode, in fact, our quantum condensate in quantum regime occupies only one single quantum mode. And if we use this approach, we can obtain this effective Hamiltonian, and this is a quantum Hamiltonian, which that is very familiar for the researchers or of Kerr-like medium and quantum properties of Kerr-like medium. But if we consider the solitons as an ansatz, in this case, it is very interesting that we obtain completely another effective Hamiltonian, quantum Hamiltonian, that is proportional to the n cube, but not n square. This is very interesting, but why this is appear? This is appear because the phase, nonlinear phase, is already proportional to the n square. This is very different. The quantum solitons or solitons, they are different from usual, for example, plane wave, chi-3 mediums, and so on. And of course, if we work with this Hamiltonian, we can obtain very interesting, some very important applications. In particular, we consider Soliton-Josephson junctions. Here you can see what is the Soliton-Josephson junctions. We consider two solitons which possess n1 and n2 number of particles, and they are weakly coupled to each other, and kappa is the coupling constant or coupling rate. And so in one dimension, this system possess soliton shape, soliton shape. In the plane of in another plane, we have just a simple Gaussian distribution for the wave function of these two coupled solitons. So particles can tunnel between these two solitons. And what is very interesting, that we I think we discover maybe some new so-called self-tuning effect. Self-tuning effect means that if we consider, for example, that effectively the coupling rate, the tunneling rate depends on the particle number. This is very interesting. And when z is equal to 1, it means that we have population imbalance between these two solitons. If z is goes to the 1, in this case, the tunneling is effectively blocked, and we have no tunneling here. So actually, effectively, this system also can be characterized by lambda parameter that proportional to the n square, but not the n, as in usual case. So of course, if you have equal number of particles in one and in the first and second solitons, in this case, effective coupling parameter is proportional to the is the same as for usual Gaussian BC. So this is this self-tuning effect is very important if we consider quantum properties of the solitons. I just remove some slide because due to the time factor. And here you can see, so this is a ground state, this is a quantum state for this SJJ model, Soliton-Josephson junction model. This coefficient can be found out by using by solution of the Schrödinger equation. And here we consider what is happened in what is happened with this coefficient. So here is a square this is a probabilistic coefficient, as the function on n. Here it is, so initially we have superfluid phase for atomic BC that characterized by the two solitons, by using two solitons. And then when lambda parameter increased, in this case, quantum phase transition occurs. Why it is quantum phase transition? It is quantum phase transition because semi-classical approach and some other approaches cannot predict this kind of phase transition at all. So only quantum approach can, if we use quantum approach, it is possible to show that in this case, it is possible to obtain superposition of the Fock states, and in part here you can see superposition of the Fock states or Nun states also, Nun states. So what is the blue color? The blue color is the corresponds to the usual, to the very usual, very common case when you have Josephson junctions with two Bose-Einstein condensates. In this case, it is possible to show, for example, Olson and collaborators, they are shown that Nun state, cat-like states, Schrödinger cat-like states occurs in the presence of this phase transition. But in our case, what is very important, phase transition give us an opportunity to form entangled Fock states and Nun states, what is very important for quantum metrology applications, but not just the cat-like states, So also I would like to mention that a scenario of this phase transition is similar to the phase transition from the superfluid to the mode insulator state. But again, I would like to mention that this phase transition appear very, very sharply due to the self-tuning of the tunneling parameter for the coupled solitons. And in particular, we also make some calculations for the Hillary-Zubairi M-order entanglement criteria, and we have shown that this in the region where this transition appear, also very high, very deep entanglement occurs, and this entanglement sometimes in some literature, for example, in the paper of Weissman and Jones, Dougherty, people call this steering, quantum steering. So quantum steering, this is some prerequisite to achieve this kind of phase transition. And also I would like to note the phase transition appear, and phase transition bring our system to the Nun state, or entangled Fock state, more correctly. Also, I would like to stress that in the region of the phase transition, we can obtain very deep planar spin squeezing. This is also important if we speak about applications in quantum metrology. So if we use these Soliton-Josephson junctions as the probe at the input of interferometer, here you can see, and if we use the relative phase between these two solitons, here you can see what we can obtain. So for the first time, it is possible to obtain it is possible to obtain in the framework of nonlinear metrology, it is possible to obtain this accuracy for the phase factor measurement, for the difference between these two solitons. And also what is interesting and what is important, it is also for the solitons, we can measure and estimate the distance between these two solitons. We can measure some momentum of the solitons. No, in particular, the distance between these two solitons is restricted by the standard quantum limit that is inversionally proportional to the n root of n. But if we use quantum properties of the solitons, in this case, the error of the propagation error for solitons displacement is inversely proportional to the n in order cube. So here you can see that all our measurements are beyond the Heisenberg limit. And now I'm going to the last part of my talk, and in particular, what is happened if we have a lossy system. For example, if we consider lossy metrology, if we consider lossy quantum metrology. So in this case, we use so-called fictitious beam splitter method. So in particular here, you can see two additional beam splitters, but in general case, they are fictitious. They are fiction because they help us to connect our interferometer, our system, with the environment. And here you can see how we can do that. This is a beam splitter, and beam splitter, some vacuum noises are also injected in this system. The vacuum noise means the coupling with the environment. So actually, currently, this, I can say, this theoretical technique, this theoretical approach, typically scientists use when we speak about metrological problems or when we speak about for example, quantum communications and quantum cryptography even. So eta here is, you can see this is a eta. Eta is transmissivity of this fictive beam splitter. And in this case, when eta is equal to 1, it means that all we have no losses in this system. But if eta is non-equal to 1, some particles are lost. And here you can see that LB and LA number of particles are lost in this system. So actually, it is very interesting to check what is happened with the null state. With I think not with the null state. The null state is collapses. This is completely evident. But what is happened with our state when we have some losses in the system? Let's suppose that initially we prepare our couplet solitons in our couplet solitons by using this state. And then, for example, we can measure one particle that is that we lost from this system. And let's suppose that we can measure that. And actually, we can see here that a superposition of the Fock state is robust on the particle losses. It's more robust. It is more robust to particle losses. And here we can see that also some small probabilities occurs even in this case is if few particles can be measured. So here you can see what is happened when we don't know how many particles we are lost, or even maybe we don't have any losses of the particles. So in any case, what is happened? This is a three-dimensional probability as a function of NA and NB. So actually, here is you can see this is a entangled Fock state. This is a blue color, corresponds to the entangled Fock state, and these two peaks corresponds to the known states at the edges of this quantum state. And then when eta is not equal to 1. It means that if some particles are lost, in this case, we can see that the null state shrinks, and we can obtain some superposition of these Gaussian-like states, which are close to the border of this plot. So in particular, we can consider with the losses. So if the losses of mechanism works, in this case, it is possible to obtain this output state. And this is more than Gaussian superposition to Gaussians of superpositions. And of course, in this limit, it is impossible to obtain very high precision of the measurement. Now, I would like to discuss that in more precisely. So here, this is a very general scheme for metrology with losses. We have input soliton quantum to soliton quantum state. Here is some unitary transformation. Here you can see that some particles can be lost. And here it is a scheme of detection and estimation. Rho is a density matrix. And finally, we can obtain some information about, we can obtain quantum Fisher information. And of course, even in this case, we can work in the framework of the linear metrology approach and nonlinear metrology approach when m is equal to 1 and m equal to 3, respectively. And here you can see a quantum Kramers-Rao bound for the Fisher information. So psi is the quantum state for the system. No, this formula is just I represent this formula without losses. Of course, if we have a losses, instead of the psi function, we need to use density matrix operators. This is obvious, of course. Nu is a number of experimental runs. And here, this is what I would like to now show you. This is our final calculations. Here you can see the ZO of the Fisher information. So this is the upper bound for Fisher information in the presence of losses. And here you can see what has happened in this system. In the present of losses, here you can see that the null state, of course, collapses. And of course, so this is the big, large picture corresponds to the linear metrology, and this picture corresponds to the nonlinear metrology approach. So in the framework of linear metrology, we have so-called standard interferometric limit which takes into account some losses. Some here, these losses can be described by the eta parameter. And here you can see that null state collapses very rapidly if so. And here you can see condition when we can use null state for quantum metrologies. This null state can be used if eta fulfill to this equation. And what is the important? It is important that, for example, if eta is equal to 0.9, the number of particles is roughly 20 and 57 for different metrological applications. And of course, even for the small number of particles, this system decohere. This system, the null state is collapses. But for the soliton, for the hour state, we can obtain different regimes which are more robust to the collapses, even in the presence of losses. So, of course, here you can see analytically we create some asymptotics. We calculate some asymptotical equations for the states and for the measurement of estimations for the Fisher information. And of course, if eta is not so large, in this case, of course, we can lose advantages in this scheme. But actually, in this region, it is possible to use coupled solitons instead of the squeeze state, for example, if we would like to enhance standard interferometric limit, even in the presence of losses. So here you can see the same plots, but for the nonlinear, in the framework of nonlinear metrology. I would like to mention that the accuracy in nonlinear metrology very high, and even for coherent probes we can achieve quite high accuracy in the framework of nonlinear metrology. Also, null states, it is possible to use null states if we consider, for example, not so large particle number. It should be 50 or less, or we need to use also very good, I can say, interferometers without any high level or some level of noises, which is of course very difficult to do. But actually, again, I would like to mention that quantum solitons, coupled quantum solitons, possess enhance the limit of the measurement beyond the Heisenberg, even beyond the Heisenberg level. So now this no, maybe I don't see, I don't speak about that so much. So actually we also estimate one body losses for the solitons and three body losses. They are non-exponential decay losses for the solitons. And actually it is very important that current experiments with atomic solitons possess or allows to use them for quantum metrological applications, because the time of observation is very short. And here you can see that within this time, it is clearly, it is possible to see, it is possible to recognize atomic solitons if we would like to create some experiment. Also, I would like to mention that recently appeared some work where people where a very famous group from US also consider collisions between solitons. And here you can see the time scale for that. And collisions between the solitons is the very important because in this case, we are able to create the phase difference between the solitons. And maybe by using this work, by using this way, it is possible to obtain Super Heisenberg limit if we would like to estimate nonlinear phase shift between these two solitons. But what is about optics? In optics, everything not so simple because in optics, typically we are deal with large number of photons, and of course we should use some technologies, some materials where quantum solitons appear for a small number of I think mesoscopic number of particles, of course. So if we consider usual fibers, in this case, the number of particles, number of photons are very huge. And of course, it is impossible to speak about null states and so on. This is not so reasonable in this limit. But for example, if we consider exciton polariton solitons in the waveguide, here you can see this is a waveguides, and this is a real experiment. And typically in this kind of experiment, we deal with a few hundred of number of photons. And because the nonlinear material is very high. Of course, dissipation is not so is not so small. And I think that in this case, it is necessary to study more precisely how quantum metrology, what has happened if we use this kind of system in photonics. But also, I would like to mention that maybe it is possible to use some, other materials. Now there exists a lot of quantum materials where we can obtain optical solitons, maybe metamaterials, and so on. So, and now I'm going to conclusion. So we propose to use quantum bright solitons with mesoscopic number of particles for quantum metrological applications. We have shown for the first time that solitons allow Super Heisenberg phase estimation up to this limit, up to this level, in the framework of nonlinear metrology approach. We propose new soliton-Josephson junction device that allows to create robust entangled Fock state, which can be modeled by the Nun state for the losses less than this number. We have shown feasibility of quantum metrological applications of quantum solitons in current experiments with atomic solitons containing moderate mesoscopic number of particles. So here I would like to show you our recent papers. And here, this is our team. We collaborate with Professor Rui-Kwang Lee from the Center of Quantum Technology in Taiwan. And here you can see PhD students who involved in this project, in the project with Rui-Kwang Lee. And actually, here you can see again, I would like to stress again our recent papers if you would like to look in more details how we can use quantum solitons for metrological applications. So thank you for your attention.
Thank you so much for the interesting talk. So please, questions, comments? Yes, Pavel, please.
Yes, can you see me?
Yeah.
I have these Bluetooth headphones and they stop working when I say something. Sorry. Yes, can I ask a stupid question? Because I think I lost a bit the physical picture. So this solitons, there are two special modes in a BEC, right?
No, yes, yeah.
Okay, so right, and then what is this interaction you're sensing? So what is the physical interaction which you sense, or the physical parameter? So you say in the linear metrology, this would be a phase difference between these two solitons.
Okay. Yes, sure. Actually, this is a good question. So in linear metrology, we use two solitons to create a Nun state, to create Nun-like state or entangled Fock state. And then we consider some phase difference between two solitons which can be accumulated during some time, for example. This is linear metrology, and the phase linearly depends on the n. So in nonlinear case, we don't need to have that. We can use just the phase difference between these two solitons. Of course, we can use some additional device that can produce some nonlinear shift, phase shift. It is possible to do, of course. It depends on what you would like to obtain, what you would like to measure and estimate. So it depends on your choice in this case.
So like in the linear case, can you think of something like an atomic interferometry, where you just have these two modes? And
yes, it is possible. Yeah, it is possible. I would like to say that, for example, even with the Mach-Zehnder interferometer, for example, people, not also me, but some people consider here some nonlinear phase shift, for example, Kerr-like medium. But in our case, we don't need that because we have nonlinear phase between these two solitons. But actually, it is also possible to take some nonlinear phase shift in this medium. It is possible to do. And otherwise, this is just the phase in atomic interferometer. Yes, okay. I agree with you.
In the linear case, and in the nonlinear case, actually, this U, what actually this sort of parameter on which things depend is this U, right?
Yeah.
So is it like, where does it come from? This atomic nonlinearity? Is it like, does it depend on collisions between the atoms? Or
yeah, this is completely true. Yes, atomic scattering lengths. The nonlinear term here you can see that. Here you can see this term just corresponds to the collisions of binary collisions of the atoms in the condensate.
So just to my understanding, so basically you say the nonlinear metrology, it's like the sensing of this of the atom density or this U parameter in some sense.
Yeah. That's true.
Okay, thanks. I think it's clear.
Okay. I see Ranjit have a question, please.
Thank you for your talk. I have two questions. The first one is, are you using cross-phase modulation effect for the generation of two solitons, A and B, or only self-phase modulation?
No, I think this is, yeah, I understand what you mean. So actually, we don't need to have additional cross-phase modulation because in particular, we have some coupled. So I think this is what your question relate to the internal and external Josephson effect. We have internal Josephson effect, and in this case, we don't need to have some cross-phase modulation and so on.
Okay. Second question is, what about the noise level? So over time,
what is
noise level?
Noise level?
Yes.
Where?
When the solitons are propagating, and then you have a noise, right?
Okay. So this is okay. So in this case, yeah, okay, I can show you this picture. Maybe you can see that. So actually, I discussed about that briefly in my talk today. So here you can see what has happened. So just can you see my picture?
Yes, I can see.
Yeah. So actually, we can measure. Sorry, we are not measuring. We don't measure anything. We calculate Hillary-Zubari entanglement criteria. When m is equal to 1, it means that this is a first-order Hillary-Zubari criteria. And first-order Hillary-Zubari criteria can be mapped onto the problem of the planar squeezing. And in our paper, you can just read about that in details. So actually, in this system, we demonstrate very deep planar squeezing at all. So if we consider n-order Hillary-Zubari criteria, in this case, we can speak about Nun state formation. And here you can see that this is green curve here. The green curve approaches to the 0.5. It means that finally we can obtain noon state according to our calculations. So, but we are not so interested in the squeezing. Of course, it is appear, but we are not interested in the squeezing. We are interested in the entangled Fock state and especially in noon state, robust noon state.
Thank you.
This is our goal of our work, how we can obtain that.
So another question, Ranjit? Ranjit, please.
Yes, I have already asked. I think third one, right now, I don't have any other questions. So thank you.
Okay, thank you. So you can. Okay. Any other questions? Okay, I have a question. Maybe you said sometimes about this, but could you summarize all of this? So how far this technique from real experiment, real technological realization? Which steps should be done to realize it? How do you think?
Yeah, I think, yeah, this is a good question. So I think, we can thought about, just a moment. So if we thought about atomic system, so I think atomic system more feasible for that, and current experiments can give us some optimism. I can say if we would like to use this kind of systems for the measurement. But in optics, I don't think that usual optical fibers can, for example, optical fibers as a care-like medium can represent some platform to obtain that, because we actually when we speak about the system should be highly nonlinear, and at the same time it should be not so noisy, not no, I think we need to obtain solitons or some chi3 nonlinear phase shifts by using not so much number of photons, thousands of photons, for example. So for me it is, or maybe less. No, actually I don't know so much materials how we can do that. So with the photons, this little bit sophisticated. So it is necessary to thought about that. Now I have no clear answer to this question. So what is about the photons?
I see. Okay.
But maybe we can use, for example, some this kind of nonlinear metrology applications a little bit in another way. For example, if we consider some circuits, photonic circuits, and maybe we consider some particles, some plasmonic particles inside the circuits, because they are very highly nonlinear. But this is some kind of sophisticated question. So I'm open to discuss that, but I'm not sure, I'm not confident that on this moment I have very clear answer for that.
I see, thank you. So let us think more about this. Okay, any other questions? I just want to note the link to the slides is in the chat, if anybody interested. Okay, so I see there are no more questions. So thank you again for your presentation. Very interesting. Hope we will find a question how to implement it.
Yeah, thank you for you, and I'm grateful to all participants of this event. And also, I would like to mention that Professor Ray Kwang Lee is also here, So actually, this work is some part of our joint project. So actually, I will be happy if you can. We are open for collaborations, and of course, I will be happy if you can find some joint topics or points where we can collaborate on this stuff. Okay.
Okay. Well, thank you.
Thank you.
See you and on our next seminars, which will be announced
thank you.
later.
So, thank you.
See you.
Bye.